Now the topic is expansion devices. So makita nyo dito yung how TXB work. TXB yung isa sa expansion devices. Meron tayong mga capillary. Tapos ito naman yung TXB. So later. So page 1. What are the purpose and types of expansion devices? So the last of the basic elements in the vapor compression cycle after the compressor, condenser, and evaporator, it is the expansion device. Okay, the purpose of the expansion device is twofold. It must reduce the pressure of the liquid refrigerant and it must regulate the flow of refrigerant to the evaporator. So this lecture contains the operation of common types of expansion devices, the capillary tube and the superheat control expansion valve, the float valve, and the constant pressure expansion valve. Yan yung mga type niya. Next slide. So, unahin natin yung type ng capillary at expansion device, which is the capillary tube. Ano dito? Capillary tube, superheat, then, okay. So, the capillary tube serves almost all small refrigeration system and its application extend up to refrigerating capacities of the order of 10 kilowatt. Ayan. Ang example ng, sige magalaw yung mouse. This is the example of capillary tube. A capillary tube is 1 to 6 meters long with an inside diameter generally from 0.5 to 2 mm. The name is a misnomer since the bore is too large to permit capillary action. Okay. Liquid refrigerant enters the capillary tube as it flows through the tube, the pressure drops because of friction and acceleration of the refrigerant. Some of the liquid flashes into vapor as the refrigerant flows through the tube. Numerous combinations of bore and length are available to obtain the desired restriction. Once the capillary tube has been selected and installed, however, the tube cannot adjust to variation in discharge pressure, suction, or load. The compressor and expansion device must arrive at suction and discharge condition which allow the compressor to pump from the evaporator the same flow rate of the refrigerant that the expansion device feeds to the evaporator. A condition of unbalanced flow between these two components must necessarily be temporary. Okay, selection of capillary tube. So, the designer of a new refrigeration unit employing a capillary tube must select the bore and length of the tube so that the compressor and tube picks a balance point at the desired evaporating temperature. Final adjustment of the length is most often cut and dry. A longer tube than desired is first installed in the system with the probable result that the balance point will occur at too low an evaporating temperature. The tube is shortened until the desired balance point is reached. So, analytical computation of pressure drop in a capillary tube. So, ito yung tube mo from point 1 to point 2. Ang delta L, yan yung length of increment. So, the equation relating states and conditions at points 1 and 2 in a very short length of capillary tube in the figure 1 will be written using the following notation. Wait, at natakpan yung ng figure. So, now, ito yung mga notations. A, cross-sectional area of the inside of the tube. Ito. With a diameter, which is the ID of the tube in meters. F, friction factor, dimensionless. S is the enthalpy, kilojoule per kilogram. S sub F, enthalpy of saturated liquid. And S sub D is enthalpy of saturated liquid. Delta L is equal to length of increment meters. P is equal to pressure Pascal. R is equal to Reynolds number. Kasi magkaibang pressure nito pang ito increment to. So, yung total length niya, so magkaiba yung initial to final. So, gagawa ka ng incremental. Yan, i-average mo yung value para makuha mo yung S of FG at very small increment. Diba yung mga numerical methods natin? Ito naman yung specific volume, B sub F, specific volume of saturated liquid, B sub G, specific volume of saturated vapor, V, velocity of refrigerant, W, okay. W yung ginamit dito na mass flow rate, X is fraction of vapor and mixture of liquid and vapor, mu, ito mga viscosity. Okay. Wait lang ah. Okay, marami kasi sa equation na gumamit ng W. So, gamitin natin yung W as a mass flow rate instead of M. Now, the fundamental applications to the control volume bounded by points 1 and 2, figure 1 is 1, are the conservation of mass, 2, conservation of energy, and the conservation of momentum. Kompleto siya, di ba? So, the equation for the conservation of mass is the mass constant, W is B1A over specific volume 1 is equal to B2A over specific volume 2. Kasi itong ano is flow rate. Divided by ng specific volume, magiging mass. So, and W over A is equal to, ito na yon, B1 over B will be constant throughout the length of capillary tube kasi yung area niya is constant. Now, the statement of conservation of energy sa Bernoulli, walang losses, walang, ano, di ba? Walang work, walang heat. This is 1000 H1 plus B1 squared over 2 is equal to 1000 H2 plus B2 squared over 2, which assumes negligibly transfer in and out of the tube. So, ito is, ang 1000 yan is for SI units yan. Tandaan nyo. So, kasi yung S1 is in kilojoules per kilogram. So, 1000 magiging joules per kilogram kasi ang labas nito is joules per kilogram. For English units, this will become foot-pounds. So, H1 may BTU per pound. So, magkakaroon ka ng factor na B1 squared over J, yung mechanical conversion ng heat, 778.16. Okay? So, remind ko lang. So, now, the momentum now involved state that the difference in forces applied to the element because of drag and pressure difference on the opposite ends of the element equals that needed to accelerate the fluid, which is P1 minus P2, fluid machinery nyo diniscuss to, at saka fluid mechanics, yata. Minus F times delta L over D, B is squared over 2 over B times A is equal to W times B sub 2 minus B sub 1. Okay. This is momentum, mass times velocity. Ito, momentum din to. Pressure times area. Mass times momentum, mass times velocity is equal to force. Pressure, force. Mass times, tama. Mass flow rate times the velocity is the equal to force, pressure times area. Di ba? Yeah. Makasabi mo, yung ano, yung force, mass times acceleration. Yung mass doon, pag mass times velocity, mass flow rate times velocity is, ang unit niya magiging unit ng force. Check nyo. Now, as the refrigerant flows to the capillary tube, take note ang refrigerant is pure substance. Its pressure and saturation temperature progressively drop, and the fraction of vapor X continuously increases. At any point, pababa, yung sa test diagram, makikita mo, tumalaki yung X. So, H is equal to H sub F plus 1 minus X plus H sub G times X. And B sub F is equal to B sub F times 1 minus X plus B sub G times X. Increment to increment, yung tubo. Pumapasok yung refrigerant doon, gas. Then, bumababa yung ano niya, pressure. So, in equation 4, B, capital B is the velocity, small letter B is the specific volume, and F all change as the refrigerant flows from point 1 to point 2. But some simplification results from equation 2 which shows that B over B is constant. So F delta L B squared over 2V, small letter B, is equal to F times delta L D B over 2, that's W over A. So in the calculation of the B used in equation 7 will be the mean velocity, is B1 plus B2 over 2. Okay, incline natin to. Yan. Now, since expressing deflection factor F for the two-phase flow is complex, hindi ito makukuha sa Modi diagram. So an approximation and later compare the calculation with experimental result as a check on the validity of this approximation built into the method. For Reynolds number in the lower range of turbulent region and an applicable equation for deflection factor F and lower range of turbulent region. That's mga 4,000, 5,000, 6,000. F is equal to 0.33 over RE. 0.25 is equal to 0.33 over BD over mu B. So, alam niyo ito, Reynolds number. The viscosity of the two-phase refrigerant at a given position in the tube is a function of vapor fraction. Mu is equal to mu F times 1 minus X plus mu G times X. Same no enthalpy sa specific volume. Now, the main friction factor po, F sub M applicable to the increment length 1 to 2 is F1 plus F2 over 2 is equal to 0.33 over RA is 0.25, 1 plus 0.33 over RA sub 2 is 0.25. Then lahat i-average mo yan, divide mo ng 2. Now, so ito na yung mga formula. Now, calculating the length of an increment. So the essence of the analytical calculation method is to determine the length of increment 1, 2. So in figure 1, for a given reduction in saturation temperature of the refrigerant. So, pag nag-reduce yung temperature mo, mag-reduce din yung pressure mo. So the flow rate and all the conditions at point 1 are known. And for a particular selected temperature at point 2, the remaining conditions at point 2 and delta L will be computed in the following step. So, computein mo siya. Mag-i-an ako ng selected na 2. So, computein mo yung length doon. Select T2. Compute P2, HF2, and F sub G2, BF2, and B sub G2, all of which are function of T2. Combine. Yung malapit doon sa 1. T1. Combine the continuity equation 2 and equation 3. So 1,000 times H2 plus B sub 2 squared over 2 times W over A squared is equal to 1,000 S1 plus B sub 1 squared over 2. Oops. This is capital. Okay. Wait. Okay. Tama pala. Kasi ito specific volume. This is velocity. This is W times B2. Nagiging over A is the velocity. Okay. Tama. Substitute equation 5 and 6 into 12. We have 1,000 times SF2 plus 1,000 HG2 minus SF2 times X plus ito BF2 plus B sub G2 minus BF2 times X over 2 is equal to W over square is equal to 1,000 H1 plus B sub 1 squared over 2. Yan. Haba. Then everything in 13 is known except X, which can be solved by quadratic equation. So solve for X, ito yung quadratic equation where A, so hindi ko nabasahin ha. Yan. B, C. Tingnan nyo mabuti. Now, with the value of X known, H2, B2, and B2 can be computed. Sinasabi natin is yung quality. Compute the Reynolds number at point 2 using the viscosity from equation 10. The inflection factor at point 2 from equation 9 and the mean inflection factor for the increment in equation 11. Finally, substitute equation 7 and 8 into equation 4 to solve delta L. Balikan nyo yung mga equation number. Hindi ko na binabanggit. So, example number 1. So, what length of capillary tube with ID as 1.63 millimeters will drop the pressure drop of saturated liquid refrigerant 22 to 40 C to the saturation temperature of the evaporator of 5 C. The flow rate is 0.01 kilogram per second. Pause mo na. Kasi ito, saturate. Okay. So given ID is equal to 1.63 mm, R22 at 40 C, evaporator of 5 C, flow rate is 0.01 kilogram per second. Require the length of capillary tube. Solution. So yan. Since the calculation will be performed on a computer kasi mag-trial and error nga tayo to facilitate the computation equation for properties of saturated refrigerant 22 applicable to a temperature range of -20 to 50 C will be used. So, abig sabihin nito, the calculation will be performed on a computer. Now, to facilitate the computation equation for properties of saturated refrigerant 22 applicable to a temperature range of -20 to 50 C will be used. Ano yon? Itong mga empirical equation na ito, and instead na mag-ano ka ng table sa isa, so meron ditong binigay na empirical equation. This is ato. Ngayon dito, hanapin niyo sa ano, yung Antoine's equation. So, ln of P over 100, natural log is equal to 15.06 minus 2.18.4 over T plus 273.15. So, ang units niya, alam niyo na, di ba? Ito, Pascal. Ito naman, Pascal yata, kilopascal liter. So, ito naman is, temperature dito is degree C. Okay? So, B sub F is 0.0777 plus 0.002062 T plus 0.00001608 T squared over 1,000. So, pag naggamit ka ng calculator, simple, hindi ka na mag-iisa-isa ng table, meron siyang applicable na formula. B sub D is equal to -4.26 plus 94050 times T plus 273.15 over P over 1,000. Then ln SF is equal to 200 plus 1.172T plus 0.001854 T squared. S sub D is equal to 405.5 plus 0.36060 minus 0.002273 T squared. So, walang plano pa. Mu sub F is equal to 0.000237 minus 1.715 times 10 is point -60 plus 8.869 times 10 is point -5 T squared. Lahat yan degree C. Bakit? Kasi nga, small letter, tapos tinagdagan ng 273. Mu sub G is equal to 11.945 times 10 is point -6 plus 50.06 times 10 is point -90 plus 0.256 times 10 -90 squared. So, lahat itong mga value, pag pinagamit sa inyo, huwag niyong irarok as is yan. Okay? Yung iba kasi yan, lagamin 0.00024. So, wag. Allow kayo, i-copy-paste yan. Huwag nyo lang ibabaguhin. Now, condition at entrance to capillary tube, point 1, the entering refrigerant is saturated, liquid at 40 C, and with X is 0. So, the properties from equation 15 to 21 are, these are for refrigerant 22 lang. So, P sub 1 is, Pascal yon, 1,536, 1,536,000 Pascal. Pressure is 40 C. Hanapin mo yung saturated yan. Saturated liquid refrigerant. 40 C. So this is, ito yan. Kuha mo yung 1,536 yan. 40 C. Diyan, based naman sa pressure and temperature niya, makuha mo H1 is equal to HF1 is 249.9. Equation 15 to 21. So B sub 1 is equal to B sub F1 is 0.000885 cubic meter per kilogram. Mu sub 1 is equal to mu sub F1 is 0.000182 T Pascal second. Yan. W over A is equal to 0.010. Yung flow rate divided by pi times 0.00160 squared over 4. Diameter to is 4792.2 kilogram per second meter squared. So, check, lagay nyo yung unit para malinaw. Dito sa pag-insert sa formula, kahit wala, tapos ilagay nyo na doon sa answer, sa result. B sub 1 is equal to W over A. Since B1 is 4792.2 times 0.000885 is 4.242 meters per second. Yan. Para na-verify mo yung unit tama. Reynolds number, R sub A1 is equal to D, B1 over mu1, B1, small letter, is equal to 0.00160 times 4.242 over 0.00001823 divided by 0.000885 is 42,850. So, yung ingatan nyo yung mga zero may mali lang kayo dyan. So, mali na. F1 is equal to 0.33 over Reynolds number is 0.25 is 0.33 over 42850 is 0.25 is 0.0229. Okay? Yung mga zero nyo. Nagkulang ka ng zero dito, tama ang sagot mo, mali ka pa rin. Sinawala yung zero mo doon. Sa 2, yung pig-try mo. So, malapit na, 40, 39. So, yan ang sinelect natin. So, dyan is P2 sa ano, may formula tayo, di ba? 1498 plus 800 Pascal. So, SF2 is equal to 248.5. S of FG2, 416.2. Yan ang units niya. B sub F2 is 0.000882. B sub G2 is 0.01533. Mu sub F2 is 0.0001833. Mu sub G2 is equal to 0.0001429. So, from equation 14, yung quadratic formula, so ang A mo doon, pag sinubstitute mo yung mga value niya, hindi ko na masyadong ano na, ang A mo is 2396.93, B is 167,992.6, C is equal to negative 1400.6. Ito yung equation. So, X is substitute mo is 0.008. Dito. Dumalaki yan. So, from 5 and 6, using an equation of the same form for viscosity, so H sub 2 is equal to S of 2 times 1 minus X plus S sub G2 times X. So, for X, substitute mo mga values, magiging H2 mo is 249.84 kilojoule per kilograms. B sub 2, ganun din, is 0.009952 cubic meter per kilograms. Kita nyo. So, mu sub 2 is ito, magiging 0.000180 Pascal second. Now, the following terms can now be calculated. So, B sub 2 is equal to W over A. B sub 2 is 4792.2 times 0.009952 is equal to 4.769 meter per second. Dato ay pwede mong Excel. Reynolds 2 is equal to dB2 over mu2. B2 is equal to number substitute values 42,918. F2 is equal to 0.33 over R sub 0.25. So, value mo is 0.0229. So, nakikita nyo naman yung mga calculation. Masyadong maba. Kaya, ano natin yung mga value na. Then, Fm is equal to F1 plus F2 over 2 is equal to 0.0229 plus 0.0229 over 2 is 0.0229. So, B sub M is equal to the average of B1 and T2 is 4.242 plus 4.769 over 2 is 4.506. Next, from equation 4, find the magnitude of the expression F sub M delta L d B sub M over 2 as B over B. Yan, dito yan sa equation. Right. So, P1 minus P2 minus delta L over dB is equal over 2. B times is equal to W plus B2 minus B1. So, this will become na. So, yung area dinivide na doon. So, this now become 1,536,000 minus 1,490,000 minus F sub M times delta L over D times B sub M over 2 times B over B. So, ito, nakita nyo, napansin nyo yan na bago. So, average saka isang octal. So, is equal to 4792.2 times 4.769 minus 4.2424. So, the expression is 34,675. And when the known values are substituted now dito, so yan. B sub 2, this is B. Ito. B over B. Diba? B over B. And this is constant. Yan, kaya pala. Kaya iniwala niya to kasi itong B over B is constant. Yan. So, this is now 34,675. So, delta L 1 to 2 is 0.2268. Ganyan. Kasam ka ng 1. Now, continuation to succeed increment. So, the conditions at point 2 that have just been computed are entering condition to the next increment of length. So, yan magiging 1 mo. In which the saturation drops to 38 C. So, 39 to 38. So table 1 presentation presents a summary of calculation near the entrance to the tube and as the temperature approaches the evaporating temperature of 5C. I-computerize mo to. The cumulative length of the capillary tube required for the specific reduction in pressure is 2.118 meter. Yan. So ito yan. So 1 to 2. Ito mag-ina mo naman. So palitan mo yung 1, yung 2. So mag-ulit ka ulit. Yung natin mong 2, 1, ang magiging 2. Yung 2, gawin mong 3. So ito na lalabas niyan. Ano yung mga value? X, dyan. Posis to 31. So, shortcut lang. Meron yan ha. Yung 36. So, 2 point. I-add mo lang to. Ito yung increment length. Tapos i-add mo yon. So, may mali dito. This is 0.2286. Wait natin ha. So, ito nga. Pinalitan ko na. 0.2286. So, 0.2286 plus 0.2013 is 0.4299 and so on. Hanggang sa maging 2.118 ang length niya. Yan. So, meron ka ng length ng capillary tube. Next, choke flow. So, table 1 shows that near the end of the capillary tube, the increment of length needed to drop 1C becomes progressively smaller. So, it might be interesting to ask what happens if the evaporating temperature is lowered, set to negative then C. So, table 2 shows continuation of table 1. So, to drop the pressure from 434.71 to 420.38, saturation temperature is -4 to -5. A negative length of capillary tube is required. So, clearly, an impossible situation has developed. So, this is now called the choke flow. Hanggang ganyan na length. So, kaya hindi ka pwede magsobra. Now, graphical method of capillary tube selection sa mga catalog. So, the first graph, figure 2, presents the refrigerant flow rate as a function of pressure to the capillary tube for a tube that is 1.63 mm in diameter and 2.03 meters long. The various curves in figure 2 represent the performance at variety of inlet conditions, magnitude of subcooling, and fluxion of vapor. Ayan, yung mga subcooling and inlet pressure. So, connect mo yun doon. Nalabas yung flow rate. This is a flow rate of refrigerant 12 or 22 to a capillary tube 1.63 mm in diameter and 2.03 meters long under choke flow conditions. So, ito. So, figure 3, the companion graph to figure 2 is 1 in figure 3, presenting correction factor to the flow rate of figure 2 for other lengths in diameter. So, for a length of 2.03 meters, dito siya, and 1.63. So, ang flow correction factor mo is 1. Pag nag-iba ka ng length, so ito, 1. So, 1 mm, tapos ito, meron ka mga 0.37. So, multiply mo doon sa flow rate. Ayan. Ang flow correction factor mo is 0.4. So, ang actual flow rate niya is nalabas dyan. Example natin. Ito, Emma. 0.47 times the flow rate nito kasi factor siya eh. So, magbababa. Diba? So, ngayon, kung gusto mong kunin yung factor, ano yung pressure mo, tapos dito, pero iba yung flow rate mo, i-ratio mo na lang. Pagkakuha mo ng ratio, hanapin mo dito. Pagka mo ratio, ano yung diameter mo? Ratio mo dito, so Kung gusto mo 1.63, so ang length mo doon is ito. Diba? Pag 0.8, so liliit. Pag 2, ito na ang kailangan mo. So, gagawa ka ng kombinasyon dyan. Both figure 2 and 3 apply to choke flow conditions. And the ASTE handbook contains further graphs to correct for non-choke flow conditions. So, sa ASTE ang reference. The length chosen that is based on choke flow conditions may be only slightly different from that needed for the non-choke flow. So, now next is the constant pressure expansion valve. So, expansion valve na tayo. So, walang picture. So, wala pa. Okay. The constant pressure expansion valve maintains a constant pressure at its outlet to the entrance to the evaporator. It senses the evaporator pressure, and when that pressure drops below the control point, the valve open wider. When the evaporator pressurizes above the control point, the valve partially closes. So, dito yung balancing, flooding, and starving tagutom. Ito tagbusog. Yeah. The effect of the valve operation on the performance of the system is charted in Figure 4. Figure 4 is the balance in unbalanced condition using a constant pressure expansion valve. The condensing pressure is constant. At condensing pressure, the compressor capacity and the feeding capacity of the expansion valve at several degrees of opening of the valve are known. Point A is the balance point. Control pressure. Ano yung balance point mo? Where the expansion valve feeds as much as the compressor pump from the evaporator. If the refrigeration load drops off, the suction temperature and pressure attempt to drop, but the valve resists the drop in pressure by opening wider. So under the new conditions, the compressor capacity remains at A. Binabalik niya dyan. But the feed rate of the valve changes to B. Yan, yung ano niya, lumalaki yung flow. The evaporator will then flood under this unbalanced flow condition, starving of the evaporator can occur if the refrigeration load increase and the valve operated at point C. Okay. Yung kinokontrol niya dyan. Use of constant pressure expansion valve has been limited to system of refrigerating capacity less than about 30 kilowatt, in which a critical charge of refrigerant is feasible to prevent liquid from flooding out of the evaporator. Its primary use is where the evaporating temperature should be maintained at a certain point to control humidity or to prevent freezing in water cooler. The pressure limiting characteristic can be used to advantage when protection is required against overload of the compressor due to high suction pressure. So, other topics na yun. Naroon tayo yung mga basic lang. Neck float valve. So, wala pa mga picture. The float valve is a type of expansion valve which maintains the liquid at constant level in a vessel or on an evaporator kasi may mga flooded type evaporator. A float switch yung mga tangke which a float switch which open wide completely when the liquid level drops below the control point and closes completely when the level reaches the control point will give the same net performance as a modulating type of float valve. 5. Balance point with various load conditions using a float valve. The condensing pressure is constant. Yeah. So under more explanation nito sa mga controls ng refrigeration. By maintaining a constant liquid level in the evaporator, the float valve always establishes balance conditions of flow between the compressor and itself. So figure 5 shows an original balance point at A. If the refrigeration load should increase, the evaporating temperature and pressure rise, which momentarily allow the compressor to pump a greater rate of flow than the valve speeding. Di ba? Tumataas. Pag wider open, tumataas yung flow. O pag narrower, miliit. Yan ang control. So, kasi ang pressure niya is same. Minimaintain niya. The valve reacts to keep the level constant by widening its average opening. A new balance point occur at point B. If the refrigeration load decreases, the suction pressure drops and the level rises, prompting the valve to close somewhat and give a balance point C. Float valve and float switch solenoid combination are used primarily in large installation. They can regulate the flow to flooded evaporators in response to the level of liquid refrigerant in the shell of the evaporator or in a chamber connected to the evaporator. This should not be used in continuous tube evaporator, which it is impossible to establish a level of liquid refrigerant by which they can be controlled. So, application ito is yung mga sa refrigerations company. Next is the superheat control thermostatic expansion valve. Normally sa air conditioner, hindi na masyado to. Sa mga refrigerating plant, kailangan to. So the most popular type of expansion device for moderate size refrigeration system is the superheat controlled valve. Superheat ang kina-control. Usually called the thermostatic expansion valve. Yung TEB. Diba? TEB ang initial niyan. The name may be misleading because control is actuated not by the temperature in the evaporator but by the magnitude of superheat of the suction gas leaving the evaporator. So, noted to the superheat expansion valve regulates the rate of flow of liquid refrigerant in proportion to the rate of evaporation in the evaporator. So, the balances of the flow rate between the compressor and the superheat controlled expansion valve are therefore practically identical to those for the float valve in figure 5. So, figure 6 is a photograph of thermostatic expansion valve. Ito yung madalas na makita at ito yung sikat na brand. Sporlan, saka yung isa pa. Yung Copland compressor. Yan. So, the superheat of the suction gas operates the thermostatic expansion valve. Tingnan nyo sa figure, sa 7. Schematic diagram of the basic superheat control expansion valve. Yan. Pillar valve from evaporator. Pillar valve kasi pinipili niya yung temperature. Kaya pillar valve. Pa-signal siya dito. So, ito na yung inlet mo. Mag-open sa evaporator. Yan, mag-adjust siya. A pillar valve figure 7 is partially filled with liquid of the same refrigerant as that used in the system. The fluid in the valve is called the power fluid. Kasi yan magpa-power dito. So the pillar valve is clamped to the outlet of the evaporator so that the valve and the power fluid closely assume the temperature of the suction gas. So the pressure of the power fluid bears on the top of the diaphragm and the evaporator pressure pushes on the bottom of the diaphragm. So a slight force exerted by the spring on the valve stem keeps the valve closed until the pressure above the diaphragm overcomes the spring forces plus the force of the evaporator pressure. For the pressure above the diaphragm to be higher than the pressure below the diaphragm, the power fluid must be at a temperature higher than the saturation temperature in the evaporator. So the suction gas must therefore be superheated in order to bring the power fluid up to the pressure which opens the valve. So, as shown in figure 8, setting superheat for normally, then valve opening. Ang super 46, ito yung equivalent niya. 100 is 7. So, as shown in figure 8, a certain amount of suction superheat is required to begin the opening the valve for C in figure 8. To overcome the force of the spring, a progressively greater force must be supplied by the power fluid to open the valve further. So this higher force is developed by increasing the superheat. Sa figure 8 shows 7K of superheat needed to open the valve completely, 100% opening. The operation of the valve maintains an approximately constant quantity of liquid in the evaporator because of if the amount of the liquid decreases, more evaporator surface is exposed for superheating the refrigerant, opening the valve further. The type of thermostatic expansion valve shown in figure 8 is of internal equalizer type, in which the evaporator pressure at the valve outlet is admitted internally to the underneath side of the diaphragm. Some refrigerating systems have an appreciable pressure drop in the evaporator or employ multiple refrigerant circuit in the evaporator, necessitating a distributor with a resultant pressure drop. Wait na, duda ko dyan. Okay, tama. So with the internal equalizer, therefore, a higher refrigerant pressure is applied to the underside of the diaphragm than actually exists in the suction line at the point where the valve is attached. This condition requires an increased amount of super heat to open the valve and reduce the effectiveness of the evaporator. Check ko lang kasi yung figure, baka mali. So, to eliminate the situation, an external equalizer ito, sabi, connect mo doon sa system din yun. Ay, yung equalizer ng mga tangke, di ba, para mag-balance siya. An external equalizer is employed which apply beneath the diaphragm the pressure of the refrigerant at the outlet of the evaporator. This process is accomplished by connecting a small tube from the suction line to the chamber beneath the diaphragm. So, as shown in the cutaway view of figure 9. Figure 9 is a sectional view of superheat controlled expansion valve showing an external equalizer. Ito yung competition niya, Alco Controls. Next is the manufacturer's rating of thermostatic expansion valve. Ito yung selection. The catalogs of manufacturers of expansion valve usually show the refrigerating capacity associated with the flow rate of which the valve is capable. Yan, flow rate and the capacity. Refrigerating capacity, yung tons, yung ilang kilowatt, ilang tons. In order to provide some reserve capacity, most manufacturers show the refrigerant capacity at perhaps 75% of the full flow rate of the pump. The flow rate to the valve is a function of pressure difference across the valve, and the velocity to the fully open valve can be computed from the hydraulic formula. Velocity is equal to C times the square root of 2 times the pressure difference in meters per second, where C is an experimentally determined constant and the pressure difference is in kilopascal. So although the refrigerant following the throttling process in the valve is a mixture of vapor and liquid, equation 22 applies to liquid because the vaporization does not occur until after the fluid has passed the valve. So, okay pa, the liquid is momentarily in a metastable condition. Wait lang. Pinopos ko. Now, electric expansion valve. The electric expansion valve shown schematically in figure 10. So, ito yung electric expansion valve. Merong voltage. Then, ito yung sensor niya. So, sensor ng flow. Uses a thermistor to sense the presence of liquid in the outlet stream of evaporator. When no liquid is present, the temperature of the thermistor increases, which drops its resistance and permits a greater current flow through the heater at the valve. The valve is thereby open, allowing an increased refrigerant flow. Yan, electronics, electrical. Application. While there is some latitude in selecting the size of an expansion valve, faulty operation results if the device is too large or too small for the installation. A valve that is too large often overfeeds or hands and may allow some liquid to flood out of the evaporator to the compressor. A valve that is too small passes insufficient liquid so that a balance point occurs at a low suction pressure, reducing the capacity of the system. Yeah. So this is the end of this topic. Expansion devices. Thank you very much.